Next section, divergent sequences. So the definition, let Sn be a sequence of real numbers we say that sequence Sn diverges to infinity as the positive integer n approaches to infinity if for any real number m, which is positive, there is a positive integer n such that nth term is greater than the positive integer m, positive real number m, and it should be true for all natural numbers n greater equal the positive integer n. So we write it as Sn converges to infinity or diverges to infinity as n tends to infinity. Here we assume this real number m being a large real number. Right? So let us see example. The sequence Sn. So let me take it as a sequence of natural numbers is divergent. Right? We have seen that the limit of this sequence does not exist. So solution to show this, given m greater than 0, consider a large real number m. So for any large real number m, we must find a positive integer n such that what? By the definition, for any large real number m, we must find natural number n such that the nth term of the sequence should be greater than the large m. It should be true for all natural number n greater than the positive integer n. That is, it means what? The nth term of the sequence is n. Right? So if we choose this large n to be greater than the real number m, large real number m, then we can have Sn greater equal m. For all n greater equal the large n, which is greater than the large m. Therefore, we can say that Sn diverges to infinity as n tends to infinity. Right? So it is a definition of, it is also a definition of divergent sequence, and the next one is also a definition, but it is the difference is it is converges to plus infinity, and it is the definition for a sequence which converging to minus infinity. So we say that sequence Sn diverges to minus infinity as n approaches to 0 if for any real number m which is positive, there is a positive integer n such that the nth term is less than minus of m. M is very large positive real number, so minus m will be negative of that large real number, so it will be very small, and we write it as Sn diverges to minus infinity as n approaches to infinity. So in this case here we assume minus m being most negative. Right? So we can have example. So I'd like to give a homework. The sequence Sn to be minus of n is also divergent, and try to solve as the above example that this sequence diverges to minus infinity. That means find value of large n so that this sequence is divergent. Right. So let me consider some other example. The sequence Sn is logarithm of 1 by n. N is positive integer, and this sequence diverges to minus infinity. So how to show? So to show this, consider for given large real number m, what we have to do? We have to find a positive integer n such that the nth term should be less than the most negative value minus m. It should be true for all n greater equal n. It means what? The nth term of the sequence is logarithm of 1 by n. It should be less than minus m. The statement should be true for all n greater equal n. It means logarithm of n, the value, so it will be minus logarithm of n by the using the property of logarithm. So it means logarithm of n is greater than m for all n greater equal n. It means n should be greater than e raised to m for all n greater equal n. So we are getting the value of n. So this will hold if n will be chosen to be greater than e raised to m. Okay. So if we choose the largest n, the value of large n to be greater than e raised to m, then we can have the nth term of the sequence will be less than minus of m. It should be true for all n greater equal n, which is greater than e to the power m. And we can say that the sequence Sn diverges to minus infinity as n approaches to infinity. The next definition. Let Sn be a sequence of real numbers. Be a sequence of real numbers If sequence Sn diverges but does not diverge to infinity and does not diverge to minus infinity, then we say that sequence Sn oscillates. That means why the sequence does not converge? Because it does not diverges to plus infinity or minus infinity, but it have different limits, right? So for example, let consider the sequence Sn to be minus 1 raised to n for positive integer n. Now since we know that this sequence Sn diverges, is divergent sequence, but definitely it does not diverges to plus infinity or minus infinity, right? Therefore it oscillates. We can have some other example. Let us consider sequence Sn to be 1 2 1 3 1 4 1 5 and so on. So this sequence is also divergent. This sequence also diverges. Since it has a divergent subsequence, which is 1 2 3 4 and so on. And the interesting thing is that but this sequence does not diverge to infinity. Why this sequence does not diverge to infinity? Because the reason is that because there is no positive integer n for which nth term is greater than 3, right? Because in the sequence, one appearing after the term alternately, right? So nth term is not greater than some fixed real number, right? Because n is appearing in between. And also the sequence Sn does not diverges to minus infinity. Why? Because again there is no positive integer n for which Sn is less than some large real number for all n greater equal n, right? So therefore Sn does not diverges to plus infinity, or minus infinity does not diverges to plus infinity or minus infinity, hence it oscillates. So let me take next example. Or I will give some assignment. So the example is, next example, sequence square root of n diverges to infinity. So how to show this? That the sequence of square root of n diverges to infinity for positive integer n. So given some large real number m positive, which is positive, and we have to find a positive integer n such that what the nth term of the sequence should be the nth term of the sequence should be greater than the large m, and it should be true for all natural number m n greater than the large n. It means what? The nth term should be greater equal m for all n. That is, n should be greater equal m square for all n greater equal n. So what value of n large n I should choose to be greater than this m square? Therefore, if we choose a positive integer to be, what the positive integer to be chosen, so that it should be greater than this m square, then the nth term of the sequence will be greater equal m for all n greater equal the large n, and large n which is chosen to be greater than m square. Therefore, we can say that the sequence Sn converges to infinity as n tends to infinity. Similarly, the next example, sequence square root of n plus 1 minus square root of n is convergent. So how to show this example? So we'll take it in our assignment. Okay. So take it as an assignment. The question is whether following sequences converges, diverges, or oscillates. The first sequence is sin n pi by 2. The second sequence is sin n pi. The third sequence is e raised to n. The next sequence is e raised to 1 by n. The next sequence is n times sin pi by n. Then the next one is sequence 1 plus 1 half plus 1 by 3 plus 1 by n. The next one is sequence minus n square. The next one is sequence of square root n plus 1 minus square root n. Okay, this much sufficient. The second thing, you have to prove that the sequence of real numbers Sn diverges to infinity, then sequence minus Sn diverges to minus infinity. The next question is that suppose sequence Sn diverges to infinity, prove that minus 1 raised to n into Sn, the sequence oscillates. Okay, this much is sufficient for the assignment.